Hello students, how are you? Today let us study about the inductive effect. This inductive effect is the displacement of sigma bonded electrons along the carbon chain towards the more electronegative atom. If a carbon chain has more electronegative group or the atom, let it be X. Because of the presence of more electronegative group, they develop some polarity between this carbon and the halogen, because we know halogens are more electronegative atoms. So, the sigma bonded electrons will move towards the halogen. So, there develops a partial negative charge on the halogen and partial positive charge on the carbon. Now, let us number these carbon atoms as 1, 2, 3, 4 from the more electronegative atom. Here a positive site is developed. Because of this development, the sigma bond pair between C1 and C2 also moves towards the more electronegative atom side. So, it is shown like this, and here this carbon, the second carbon also develops a partial positive charge and it continues to the third carbon also. So, this sigma bonded pair also moves towards the right side. So, here also it develops a partial positive charge, and after third carbon the inductive effect is negligible. So, inductive effect is distance dependent. Distance dependent. Inductive effect is distance dependent. With the increase of the distance between the carbon atom and the halogens, the effect of inductiveness, the inductive effect decreases. Okay? And this sign, delta sign, indicates the position from the more electronegative atom. Okay? This is the displacement of sigma bonded electrons along the carbon chain, which is known as inductive effect. Inductive effect is two types: plus I effect and minus I effect. Plus I effect and minus I effect. Plus I effect is caused by electron releasing groups. Electron releasing groups cause plus I effect. Electron releasing groups are alkyl groups, mostly alkyl groups. With the increase in the number of carbon atoms in the alkyl chain, the plus I effect also increases. That means C2H5 greater than CH3, or ethyl group shows more positive inductive effect over the methyl group. With the increase in the number of carbon atoms, plus I effect also increases. And minus I effect is caused by electron withdrawing groups. That means electron attracting groups. Which groups will attract the electrons? The groups with more electronegativity. The halogens and OH group and amine group, all these will attract the electrons. If these groups are present on the carbon chain, they show the negative I effect. And with increase in the electronegativity, with increase in electronegativity, inductive effect minus I effect also increases. That means if we see the halogens, fluorine, chlorine, bromine and iodine. Fluorine, chlorine, bromine and iodine, which will have more negative I effect. We know that fluorine has the maximum electronegativity. So, fluorine shows maximum minus I effect than chlorine, than bromine, than iodine. And this point can be explained by taking the hybridization also. sp carbon will be more electronegative. We know very well, with the increase in the percentage of S character, the electronegativity increases. sp carbon greater than sp2 carbon greater than sp3 carbon. this also can be explained. If these carbon atoms are present in a group of substances, then also we can explain which will have the more negative I effect. And if we have this kind of groups, fluorine, hydroxyl ion, NH2 and CH3. Fluorine is more electronegative than OH, oxygen, which is more electronegative than nitrogen, NH2, which is more electronegative than methyl group. Okay. So, these are the negative minus I effect causing groups which are more electronegative groups. Now, let us see what are the applications of inductive effect. The important application of inductive effect is the acidic nature of different carboxylic acids. How the different carboxylic acids will exhibit different acidic strength. What is the strength of different carboxylic acids? Let us see now. Here I have taken different examples. In the first set, methanoic acid, ethanoic acid and propanoic acid, the number of carbon atoms is increasing. Now what happens? We know that the alkyl groups are electron releasing groups. In this, there are two alkyl groups which increase the electron density on the carboxylate ion. If it has to show the acidic nature, it has to lose the proton. On losing the proton, when it loses the proton, when there is a less attraction between the oxygen and hydrogen, this hydrogen can be easily eliminated. Okay, but here these alkyl groups are increasing the electron density. The displacement of electrons is towards the more electronegative oxygen. So, this hydrogen is more strongly bound to the oxygen, which decreases the acidity of this carboxylic acid. So, it is less acidic, and if we see the acetic acid, it has one methyl group. It has one methyl group, then this is ethyl, this is methyl. So, the displacement of sigma bonded electrons is less when compared to propanoic acid here. So, this proton can be a little more effectively eliminated, removed. So, acetic acid is more acidic than propanoic acid. If we see the formic acid, that is the methanoic acid, there are no alkyl groups. So, this proton can be easily eliminated. So, formic acid is more stronger than acetic acid, which is ethanoic acid, and which is more stronger than propanoic acid. The strength of acid is explained by the ease with which an acid eliminates its proton. Okay. So, among these three, formic acid can eliminate its proton more effectively. So, it is more stronger than ethanoic acid than propanoic acid. Coming to the next example, here alpha fluoroacetic acid, alpha chloroacetic acid, alpha bromoacetic acid and alpha iodoacetic acid. We know that with the decrease in the electronegativity, the inductive effect also decreases. From fluorine to iodine, the electronegativity is decreasing. So, fluoroacetic acid is more stronger acid, because here the sigma bonded electrons will move towards the fluorine. Here fluorine will attract the electrons towards itself. So, this proton can be easily eliminated. Therefore, the alpha fluoroacetic acid is more stronger acid than alpha chloroacetic acid, which is more stronger than alpha bromoacetic acid, which is more stronger than alpha iodoacetic acid. Okay. Next, number of halogens on the alpha carbon. There are three halogens, three chlorine atoms on the alpha carbon. These electrons will be displaced towards the chlorine atom. So, this proton can be easily eliminated. And in the second structure, only two chlorine atoms are present. So, the displacement is towards the chlorine atoms is less. One chlorine is less on the alpha carbon. So, it will be less acidic when compared to the trichloroacetic acid, and which is less acidic than monochloroacetic acid, which is less acidic than normal acetic acid. Okay. So, it is greater than sign. And here in the fourth case, it is inductive effect is distance dependent. This chlorine is present on the alpha carbon, and in this chlorine is present on the beta carbon. So, the sigma bonded electrons will move towards the chlorine atom in the first case and in the second case also, but the inductive effect is less in the second case. So, the negative charge is moving towards the chlorine here. So, this proton can be easily eliminated. So, it is more acidic. Alpha chloropropanoic acid is more acidic than beta chloropropanoic acid, because the distance from the electronegative atom to the proton transfer is increasing from alpha chloropropanoic acid to beta chloropropanoic acid. Okay, students. The second application is the basic nature of amines. Amines are basic in nature. What is basic nature? The ease of donation of electron pair. That is the basic nature. Now here, this is primary amine, secondary amine and tertiary amine. There is one lone pair of electron on the nitrogen atom. We know very well. Now here, there is one methyl group here, two methyl groups and three methyl groups, which will be more basic. In this tertiary amine, this is tertiary amine. We know that alkyl groups are electron releasing groups. So, they increase the electron density on the nitrogen. So, this electron pair can be easily donated to any acid. So, electron pair donor is a base according to Lewis theory. So, with the increase in the number of alkyl groups, the electron donating capacity of nitrogen increases. The property of electron donation by the nitrogen increases. So, it is more basic when compared to secondary amine, which has only two alkyl groups, and it is more basic than primary amine. So, what is the order? Primary amine less basic than secondary amine, which is less basic than tertiary amine. Okay. Now, coming to ammonia. Ammonia has no alkyl groups. No alkyl groups. So, this ammonia is less basic than even primary amine. Ammonia is less basic than primary amine. Primary amine is more basic than ammonia. That means ammonia comes here before the primary amine. If we compare the basic nature of aliphatic amines, ammonia and aromatic amine, that is aniline, what happens? Now here this ammonia has a lone pair of electron on nitrogen, and aniline also has a lone pair of electron, but here this lone pair is taken by the benzene, because benzene ring is an electron withdrawing group. So, this lone pair will participate in the resonance of the benzene ring. So, this lone pair is not available to the nitrogen for donation. So, aniline is less basic. Aniline is less basic than even ammonia, because the lone pair is here not available, here lone pair is available. So, ammonia is more basic than aniline. Okay, students. Now, let us see some more examples, students. Here it is benzoic acid, para-nitrobenzoic acid and para-methyl benzoic acid. This benzoic acid is neutral, nitro group is electron withdrawing group and methyl group is electron releasing group. So, this benzoic acid comes in the middle, that means A comes in the middle, and what is the effect of this nitro group and methyl group? This nitro group withdraws all the electron density towards itself, so that the elimination of this proton is more easy. Therefore, B is more stronger acid than A, and as this methyl group is electron releasing group, it increases the electron density on the benzoxylate ion. So, the ease of removal of proton is less in this case. So, C is less acidic, B greater than A greater than C. This is the order of acidic strength of these three structures. If we see the next set of structures, that is orthonitrophenol, metanitrophenol and paranitrophenol. Any groups if present on the meta position, the effect will be very less. Here the nitro group is present at ortho position. We know that inductive effect is dependent on the distance. Here these are more closer, so all the entire electron density moves towards the nitro group. So, the ease of elimination of proton is more in this case. Now, coming to the para structure, the distance between nitro group and hydroxyl group is more. So, even though the electron density moves, the effect will be less. So, this is less acidic. Paranitrophenol is less acidic than orthonitrophenol. A is more stronger than C, which is more stronger than B. Okay, students. Now, coming to the next set of examples, FCH2COOH. This is alpha fluoroethanoic acid. This is alpha diiodoethanoic acid. There is one point here which we have to remember. When we see the fluorine and electronegativity of fluorine and iodine, fluorine is more electronegative, that point we know very well. So, we will expect that alpha fluoroethanoic acid will be more acidic than this alpha iodoacetic acid, but here there are two iodine atoms. Any two halogens are more effective than even fluorine. So, the electron density moves towards the iodine atoms in this alpha diiodoethanoic acid more strongerly than alpha fluoroethanoic acid. So, alpha fluoroethanoic acid is less acidic than alpha diiodoethanoic acid. Okay, students, hope you find this video very useful for all the entrance examinations. So, all these applications are very useful. Okay, students.